Welcome to qnawire.
All right, so it should be recording now. Let's get right into the problem. So I'm just going to draw my axes here. Oh. Try to make it as straight as possible. Sorry for this drawing. I don't have a mouse adapter for my Mac, so you just have to bear with me. All right, so the problem is that we have a semicircle of a special charge distribution, and essentially we want to know the magnetic field, or not the electric field at the origin. So how do we go about this? Well, from university physics, we should know that positive charges are going to emit an electric field, so radially outwards, kind of like this. Too close to the top there. Radially outward, while negative charge will have an electric field of radially inward. So if we look at the arc, if we say the charge is focused at the center of the arc, let's say the left of the y-axis, the positive charge, we'll have an arrow here, and that can define our positive electric field contribution. For the negative, we can do something similar. And as I said, it was radially inward, right? So it should be here, E minus. Right. So as you can see, these vectors are both in the x and y plane. So if we write out the components for them, we'll see that only the x component survives, because you have a positive y x component for the for the negative charge, but you have a negative y x component for the positive charge. So if you're not convinced of this right now, the math should convince you later, but that is what should happen. We should see that there's only an x component of the electric field. So let's look at that x component. So if I just write x here, generally an electric field will be written like kq over r squared. But in this situation, we have a kind of special charge. We don't have point charges, we have a line of charge, right? So we need to use a special symbol lambda to define that we call the linear charge density. So lambda is, as you could guess, charge per length. So this is what we mean when we say linear charge density. But it is a curved line, right? And so basically what we're going to have here is we have to try to figure out what L is, right? So let's say that we had a full circle. So I'm just going to claim that if we're just focused on one part of the arc, then well, oh no, it's not one part of it. We want the whole arc, right? So this is a semicircle is going to be half of a circle, right? And so the length of a full circle is going to be the circumference. But oh yeah, we will focus on just this contribution, for example, just the positive contribution. So this is a fourth of the circle, right? So if L is defined as the well, if L of a full circle is the circumference, right, the length of the perimeter of the circle, 2 pi r, and we take a fourth of that, like the positive Q region, so we just want to divide by 4. And we should know that the radius is a, which I didn't write earlier, but that is in the problem as well. Semicircle of radius a. Then r is going to change to a, and then we'll see that 2 and 4 cancel, and we'll have pi a over 2 as the length. So we plug that in for L, and we should see 2q over pi a. Or, yeah, 2q over pi a. Yeah, I wrote this incorrect. This is not L divided by 4. This would be L equals C divided by 4, right? Circumference divided by 4. The length of one. So this is the L is the length of one arc. It's, half of the arc. So we can start to look at the electric field so we can find out the magnitude and direction, right? So I'm just going to make a new page here. So let's look at the x component of the field, the electric field. So if we go back to the first page real quick, then we can see that we need to replace Q over R in this electric field with a lambda, right? Q over some distance. So we can say electric field is going to be K lambda over R. But as you could guess, there's electric fields, there's an electric field coming from each angle, from all angles, at least from, if we're saying this angle is, the x-axis is 0, then this would be where the y-axis is, which would be pi over 2, just following like the unit circle convention, reading theta from the x-axis counterclockwise, and then this would be theta equals pi. So from pi to pi over 2, we're going to have positive charge electric field contribution. And from pi over 2 to 0, we'll have negative charge electric field contribution. So with that in mind, and that the angle is going to change, so we need to account for that. So we'll write our first part here, k lambda over r, but of course our radius is a, so I'm just going to write a here. Then we actually want to have an integral, right? So we want to integrate cosine theta. So integrate cos theta d theta. Now we have to figure out which, so if this is going to be our positive contribution, right? I said it was going to be from, oops, that's not what I wanted to, okay. This is going to be from pi over 2 to pi, right? So this is what our integration bound would be, pi over 2 to pi. And we'll have something similar but negative for the negative charge contribution, right? So let's just write that out quickly. Cos theta d theta. But now we're going to be going from 0 to pi over 2, right? Because that's where the negative charge is. So these are pretty simple integrals to evaluate, right? So if we just pull k lambda over a out here and try to evaluate these integrals, we know that the integral of cosine is just the same thing as asking what function gives me cosine theta when I take the derivative of it, right? So that should be sine. So we can write here sine theta evaluated from pi over 2 to pi. And then we will subtract the same thing, but now with different bounds. 0 to pi over 2. All right. So this should be pretty simple here. If we look at sine of pi, what is that going to be? Well, on the unit circle, if theta is equal to pi, then there's no y part, so it's going to be 0. So, and then sine of pi over 2 will be 1, right? Because that's the top of the circle here, as we can see. It's going to be a 1. So what does this mean for the first part? So the first one is going to be 0 minus 1. So we'll have a minus k lambda over a for the first part. And what about this pi over 2 to 0 sine theta? So like I said before, sine of pi over 2 is going to be 1. And sine of 0 is the same as sine of pi, also 0. So if we subtract 1, then we should just see another contribution of minus k lambda over a. So we just have minus 2k lambda over a as our complete x electric field contribution. Okay, so let's look at the y. In case you weren't convinced before, let's just really quickly, let's look at this. So we do the same thing here. We're dealing with a component of a vector, right? So we need to include the angle. But rather than using cosine now for x, we want to use sine for y, right? So same bounds, but now we just switch the function inside. Now we're just going to have sine theta d theta inside instead of cosine theta d theta. All right, and so just to think about this one really quickly. The integral of sine theta, we're going to ask the same question we did before. When you take the derivative of something, what is it that's going to give me sine theta? Well, the derivative of cosine theta is minus sine theta. So to get a positive sine theta, we're going to need a negative cosine, right? So let's begin writing here, k lambda over a, just pull that out. So this is actually going to be minus cosine theta evaluated at these bounds, pi over 2 and pi, minus another minus cosine, right? Evaluated at 0 and pi over 2. So that will be our full answer. So let's go through each of these 4 bounds and find what the numbers are. So a lambda over a, the first part is going to be minus cosine of pi. So cosine of pi is going to be minus 1. So this is minus minus 1. You want to subtract when you're evaluating these bounds. So it's going to be minus minus cosine, so it'll be plus cosine theta, or plus cosine of pi over 2, but we know that that's 0, right? So there's no contribution here. And we'll subtract again, this middle subtraction. Evaluating minus cosine of pi over 2, which we just said was 0 earlier. But then we're also subtracting cosine of 0, which is going to be just 1, right? Yes, just 1. So that looks like it's going to actually give us something, which is not right. So minus on the minus 1 should be positive 1, and then subtracting minus 1 is going to add, and that gives you plus 2. That's not right. Okay, let's go back here. Okay, I think I had the sign right in the middle there. This should be plus, actually. Plus minus cosine theta, not minus minus cosine theta. Sorry about that. 0 pi over 2. Okay, so now let's do that again. That's real quick. We have k lambda over a. Just like I said before, so this is minus cosine of pi. That's going to be minus minus 1, so just a positive 1. Cosine of pi over 2 is 0, so we don't need to worry about that. Plus minus cosine of pi over 2 is 0. And then minus minus cosine of 0 should just be 1. So we should see 0 here. So like I said before, there's no y electric field contribution. Or no, okay, that was right. So the minus came from here earlier. So this minus should follow through. So this actually is a minus. This is minus, which is basically going to make the whole thing plus, right? That'll be plus, which lets well, the electric field in the y should be 0 in any case. One second here. Yeah, so that should be minus. Yeah. Anyway, now that we have the x from page 2 here, this 2, to find the net electric field, we just want to use the distance equation like normal. So this would be E net is the square root of the x component and the y component. But like we said before, we have no y component. So basically it's just the square root of ex squared, which essentially just makes it positive, right? So we should just get something like well, let's work it out. Let's see. Minus 2k lambda over a squared will be 4k squared lambda squared over a squared. Then we have to have the square root. Then we get 2k lambda over a. Right? So the net electric field is just going to be 2k lambda over A, where K is going to be equal to 1 over 4 pi epsilon naught and lambda we defined earlier as 2q over pi A, our linear charge density. So you can plug those in and find, you can simplify this net electric field. So this is our answer here. And that direction is going to be positive, right? Because as we could see from the this picture, we'll have positive contribution from the left and then negative contribution from the right. And so this is our vector here. So that's our magnitude and direction.